This is our second video for transition metals for chapter 24, and in this chapter we're going to be looking at naming transition metal complexes and the isomers that they form. So first of all, we're going to start off by looking at naming coordination compounds. And the first thing we need to do is to determine the name of the non-complex ion. After we do that, then we determine the ligand names and list them in alphabetical order. Then we determine the name of the metal cation. Then we name the complex ion by name each ligand alphabetically, adding a prefix in front of each ligand to indicate the number found in the complex ion. Then we follow with the name of the metal cation. Lastly, we write the name of the cation followed by the name of the anion. So here we're looking at this aluminum complex. So remember, everything inside the bracket is the complex, and this is the ligand, the oxalate ligand that binds to the aluminum. So the potassium here, this is just balancing out the charge, and it's not actually bound to the metal. So if I were to draw a picture of this, so we have the aluminum, and we have three oxalates bound to the aluminum. So I've kind of taken a shortcut. So these are the oxalate ligands, where the oxygens are the oxygen portions of this. So in this formula, we write the cation followed by the anion. And the potassium, there are three potassiums. So there are three potassium ions in solution to balance out the 3- charge for this aluminum complex. So it's cation, then anion, so potassium trioxalato aluminate. And as we name the complex ion, we list the ligands first. So the oxalate ligands are the oxalato ligands, and tri means that there are three of the oxalate ligands bound to it. So the name is potassium trioxalato aluminate. Now, because this cation is negatively charged, this is an anion, we change the ending from aluminum to aluminate. And the 3 indicates the oxidation state of the aluminum, so there's a +3. So the oxidation state of the aluminum is +3, and the oxalate ligands have a charge of -2 each, but there are 3 of them there. And then there are 3 potassium. So if we weren't sure what the oxidation state of the aluminum, this is how we could figure this out. So I know that there are 3 potassiums, and each potassium has a +1 charge. I don't know the oxidation state of the aluminum, so I'm going to put X for it. And I also know that there are 3 oxalate ligands, and the oxalate ligands have a charge of -2. And then the overall charge for everything is 0. So when I solve for this, so 3 plus X minus 6 equals 0, well then X must be 3. So that's where I get the oxidation state of that aluminum. Let's say we have a cation for a complex, for a metal complex. This is dichloro bis ethylene diamine cobalt 3 sulfate. So the sulfate is our counter ion, and that has an SO4, so that's a 2- charge. And because there are 2 chlorides, so this is a dichloro, so the chlorine becomes a chloro when it becomes a ligand. The bis means that there are 2 ethylene diamines attached to it, so EN is just an abbreviation for ethylene diamine. And so we go in alphabetical order, so C comes before E, so the chlorine ligand is listed first, so the chloro ligand is listed first, and then the ethylene diamine. So when I look at this, I've got to figure out the charge or the oxidation state of the cobalt. And the sulfate, so let's go ahead and do this. The sulfate has a -2 charge, and there's only one of those. The ethylene diamine ligand is neutral, so there are 2 of those, and each one of those gets a 0. there are 2 chlorides, and each one of those gets a -1. And then X for my cobalt. So I'm going to show that that all adds up to 0. Oh, but I have to be careful here. Notice that there's a subscript 2 here. That means that there are 2 of these complexes. So let me back up. I'm going to scribble this out. Let's erase some of the board. So I'm going to determine the oxidation state of the cobalt again. So there are 2 of these complexes, but each one of those complexes has a +1 charge. So I'm just going to write one of those here. So each one of those has a +1 charge. So if I don't know the oxidation state of my cobalt and put an X for it, there are 2 chlorides which are each -1. The ethylene diamine is neutral, so that gets a +0. And the overall charge is +1, so all has to add up to the overall charge. So X minus 2 equals +1. So I'm going to add 2 to both sides. So X must be +3. So that's where I get the oxidation state of my cobalt. Now if I were going from the name to the formula, so here it's potassium, so my potassium is first. And then my aluminum, so my metal part comes before the ligands in the formula. And there are 3 oxalato ligands, so there are 3 of these oxalato ligands. Now in the name, notice here with the potassium, it doesn't tell me how many potassium I have. But because I know the oxidation state of the aluminum, because it's given here, I can figure out the overall charge of this trioxalato aluminate. And that trioxalato aluminate had this whole thing here has a charge of 3-. Well, I don't need to say that there are 3 potassiums here in the name because it would be redundant information because the potassium has to neutral out the charge. So there are actually 3 potassium here. So I show the 3 potassium in the formula, but I don't necessarily show it in the name when I name it. Now I know the naming can get complicated, but for our exams, you'll just have to be able to recognize the correct name from a list of possibilities from the multiple choice. Because in reality, the naming for transition metal complexes is much more complicated than what we've just shown here. But we'll just be sticking with mainly some simple complex ions. Now remember when we had the chloride and we called it the chloroligand? So the ligands change name when they bind to a metal. So the bromide becomes bromo, the chloride becomes chloro, hydroxide is hydroxo, cyanide becomes cyano, nitrite becomes nitro, and the oxalate becomes oxalato. And here you can see the charges of the ligands. Now here are some of the neutral molecules, such as water. It becomes the aqua ligand. Ammonia, this is a little bit weird. For some reason it has a big name change. It goes from ammonia to amine. Carbon monoxide becomes a carbonyl. Ethylene diamine is still ethylene diamine. And ethylene diamine tetraacetate becomes ethylene diamine tetraacetato. Now we want to start looking at how do we classify isomers. And isomers are 2 or more molecules or ions with identical formulas, but things are arranged differently or bonded differently, and it gives unique properties to the way that things are put together. So they have the same pieces, the pieces are just arranged slightly differently with the isomers. So as you start trying to figure out what type of isomer something is, the first question is, are the bonds between the atoms the same? And if they are the same, then we're looking at stereo or configurational isomers. And then the next question is each identical to its mirror image? So if we produced a mirror image, could you overlay them? If yes, they are diastereomers or geometric isomers. If no, they're enantiomers or optical isomers, so chiral or non-superimposable mirror images. But let's say the bonds between the atoms aren't the same. Then these are going to be structural or constitutional isomers. And we're going to be looking at 4 different forms of structural isomers. We'll look at ionization isomers, linkage isomers, coordination isomers, and then hydride isomers. So we'll look at the structural isomers first. So let's start off with the ionization isomers. Ionization isomers are those that give different ions when dissolved in water. So ionization isomers occur when a ligand and a counterion in a compound change place. So for this example here, we've got 2 different cobalt complexes. They both have 5 amines, they both have a bromine, and they both have sulfate. But they're arranged a little bit differently. One produces a red-violet color and the other produces a red form. So with the red-violet form, if I were to add barium to this, what would happen was the barium would combine with the sulfate and you'd get a white precipitate. And what this tells us is that the sulfate originally isn't attached to the cobalt complex. It was free in solution. So what that means is that the cobalt had to be bound to the bromine, so the bromo ligand, and the 5 amine ligands to make a cobalt complex with a 2+ charge. So if I were to write the formula for this, this would be barium with a cobalt, Br, and then NH3, 5, because what's in the brackets are what's actually bound to the cobalt. And here, oops, sorry, that shouldn't have a barium right there. Barium is what I added to solution. The sulfate is the counterion. So if this has a 2+ charge for the cobalt complex, the sulfate has a 2- charge in it. They balance each other out. So this would be the formula for this compound here. Now, this isomer here, which is red in color, if I add silver to it, silver bromide will precipitate out. And that tells me that there are free bromides in solution, and when I add the silver, they'll combine together to make silver bromide. It'll precipitate out. And what that tells me is that in solution you have this cobalt complex. So whereas in the red-violet form the bromide is bound to the cobalt, in the red form the sulfate is bound to the cobalt. So the formula for this complex would be the cobalt with the SO4 and then the 5 amines. And it has a +1 charge, and then to balance out that +1 charge is the bromide. So you have different things that are ionizing. The sulfate and the bromide have changed places. So here the SO4 was in solution, balancing out the charge of this 2+. Here the bromide was balancing out the charge of this complex solution. Now linkage isomers are the same ligand, but it binds through different atoms. So the nitrite actually is an ambidentate ligand, so it can bind either through the oxygen or it can bind through the nitrogen. So using UV light you can actually switch it from the nitrito form, so this is where it binds through the oxygen, to the yellow form where it binds to the nitrogen. So just by that simple switch of changing how the ligand binds to it, we get different colors for the complexes. So that's actually really kind of cool. So here we have the ligand bound through the oxygen, and here we have the ligand bound through the nitrogen. So it's linked differently to the metal. That's why we call it a linkage isomer. Now coordination isomers, the total ratio of ligand to metal remains the same, but the ligands attached to a specific metal ion change. So here we're looking at this empirical formula for platinum where there's a 1 to 2 ratio of the platinum to the amines and a 1 to 2 ratio of the platinum to the chloroligands. And these three compounds are all coordination isomers. You still have a 1 to 2 ratio of the metal to each ligand. Now this platinum complex, here's a platinum complex with 3 ammonias attached to it and 1 chlorine, and another platinum complex with 1 amine and 3 chlorides, but they're balancing out the charge on each one. So this compound apparently has not been reported, but the individual ions are known. But Magnus's green salt, this one still, you still have a 1 to 2 ratio. So you've got 1 platinum here and another platinum here, so that's 2 platinums for every 4 amines, so you still have that 1 to 2 ratio. So these are coordination isomers. Now hydration isomers have different proportions of water molecules coordinated between the different isomers. In this example we have a chromium with 3 chlorides and 6 waters. In the violet form, all 6 waters are bound to the chromium. In the light green form, there are 5 waters and 1 chloride bound to the chromium. And in the dark green form, there are 2 chlorides and 4 waters. So just by changing what's bound to the metal, you get very different colors. Now you can actually distinguish between these two by either using a physical measurement or a chemical test. And a physical measurement is basically if you're measuring the conductivity of the solution. Because when this dissolves, it'll produce the chromium complex, so that chromium with the 6 waters, and then it'll produce 3 chlorides. So here you'll have a total of 4 ions in solution. When this compound dissolves, you get the chromium complex and the 2 chlorides, so you'll get 3 ions in solution. And when this compound dissolves, you get the chromium complex and the 1 chloride, so you get 2 ions in solution. So if I were to measure the conductivity of these solutions, I would expect this solution to conduct electricity better than the solution that has 3, and the 3 to conduct electricity even better than the solution that has 2 ions in it. So just by measuring how well the solutions conduct electricity, I can figure out the number of ions in solution. I could also do a chemical test. So remember when I added silver to the, I believe it was our ionization isomer. If I add silver to each one of these and I titrate it, I can figure out the amount of silver chloride that's produced. So this one would produce 3 equivalents of silver chloride solid. This would produce 2 equivalents of silver chloride solid, and this would produce 1 equivalent of silver chloride solid. So I could titrate it with the chloride and precipitate out the chloride, the silver chloride complex, to figure out how much is in solution. Because the silver chloride has a very poor solubility. And you're going to be taking advantage of this when you do the qual scheme in lab. So if you have a silver ion and you add HCl, so it's a source of chloride ions, the silver chloride will precipitate out as a white solid. Now let's look at the geometric isomers. Geometric isomers are stereoisomers that differ in the spatial orientation of the ligands. So the same things are bound to the metal, they're just arranged differently about the metal. So if we have square planar complexes, you can have cis or trans arrangements. Cis simply means that they're on the same side of the metal. Trans means they're on opposite ends. And you can also have cis and trans isomers for octahedral complexes. So here we have 2 things right next to each other for this cobalt complex. So this would be the cis isomer. And if those 2 things are on opposite sides, those would be trans. So you can only have two of the same thing, and they have to be opposite to each other to be trans, and only two things that are the same that are right next to each other to be cis. Now another type of geometric isomer that you're going to find, these are only for octahedral complexes, and they are called the FAC and the MER isomer. So the FAC stands for facial. So if we look at the face of this octahedron, all of these ions that are the same lie on the same face of the octahedron. The MER stands for meridional. These all lie in the same plane as the metal ion. So think about if we had a globe like the prime meridian. So these are all in the same plane as that metal center. So again, just looking at cis and trans isomers. So this would be a cis isomer. This would also be a cis isomer. And this would be a trans isomer. So cis again means two things right next to each other. Trans means they're on opposite sides. And you can get cis and trans with either square planar complexes or with octahedral complexes. Again, we're just looking at the FAC versus the MER. So for the FAC and the MER, you're only going to see this for octahedral complexes, and you have to have at least three things that are the same. So these B ligands form the facial isomer, and these B all form a triangle here with the central metal, and this is the MER isomer. So FAC means facial, a set of three atoms that lie on the face of the octahedron. And MER is meridional, a set of three atoms that lie in the same plane, and that plane contains the metal. Now, optical isomers are stereoisomers that are non-superimposable mirror images of each other. So let's say I have a mirror here, and this molecule is looking in the mirror. The molecule sees its reflection. So this is the reflection of this isomer here. But if I were to try to take this isomer here and overlay it with this original picture, notice that it doesn't look exactly the same, because in this one, this is our delta isomer. Notice that the ligand has an attachment on the right hand side, but it's missing that in this lambda isomer. So we can't superimpose, we can't overlay these together for them to look exactly the same. So these are stereoisomers of each other. And a lot of biological molecules are chiral like this. They are non-superimposable mirror images, kind of like your hands. If you look at your hands, they're mirror images of each other, but you can't overlay them so that you can't see the bottom hand. So in the delta one, you look at the top ligand, and as you follow it down, it goes back into the right, so that's the delta form. And the lambda form is when it goes to the back and to the left. And this is just different ways of looking at the delta versus the lambda. So remember, the delta is to the right, lambda is to the left. So that ends video 2. And in video 3, we'll be looking at crystal field theory, colors,